One of the projects I'm currently working on is the Monitoring Atmospheric Composition and Climate project, which is currently in its third phase. MAC establishes the pre-operational services for what will become the Copernicus Atmosphere Monitoring Service in 2015. What MAC does is to take all available satellite information regarding atmospheric composition, aerosols and trace gases, elaborate it with the aid of a powerful computer to produce then an analysis of the state of the atmospheric composition, and from that to do a prediction up to 5 days ahead of what the state of the atmosphere will be. Here's a picture illustrating an aerosol forecast. So this is a model simulation, which is based on data from the MODIS sensor of aerosol optical depth that are elaborated, and then the model adds information to the satellite data by then giving us details about the various species, aerosol species. For example, here you see some biomass burning over Africa, desert dust here into the Mediterranean and going off to the Atlantic. You see marine aerosols, sea salt, quite a bit in the southern hemisphere. You even see this nice feature like a cyclone. And then you see also the sulfates, more anthropogenic aerosols. And this is what MAC produces. And along with this, we have also prediction of other constituents, for example, carbon monoxide, CO, NO2, and ozone, and also carbon dioxide and methane. Some instruments, for example, the so-called imagers, they look at the refracted solar radiation, and they sense mainly clouds, aerosols. They can give information about surface characteristics, surface albedo, and those are the visible images. Then you have a set of sensors, still passive sensors, that instead measure, if you want, the temperature of the planet, and they also, because they sense, they emit radiation, but in the infrared spectrum. So this is not the visible part, but the infrared part. And some trace gases, you can see the signature of these gases in the infrared part. For example, CO2, CO, and ozone, and other trace gases, methane. So you use the infrared part of the spectrum to sense the atmosphere. You can also go to microwave wavelengths, and you also get other information about other parameters, including precipitation, for example. So aerosols are interactive with the radiation that comes from the sun to the earth, also with the radiation that comes from the earth and is emitted back to space. And because of this, it's possible to sense them from satellites, because satellites sense the radiation. And then you can infer properties about the aerosols through analysis of this radiation that the satellite has sensed. And that is extremely important in my job, which is that of predicting the aerosol state with few days ahead. And I use the satellite information, the observations derived from the satellite, to initialize the model and constrain the model so that the prediction is as accurate as possible or as close as possible to current observations of the state of the aerosols in the atmospheres. And a similar thing is applied to other trace gases, ozone, carbon monoxide, as well as observing wildfires and emissions of carbon dioxide and biomass burning from fire. So it's the same principle.